In this video I'm going to talk about IEC 60909 Method C for calculating the DC component of a short circuit current. The main driver for calculating short circuit currents in power systems is safety. All equipment in the power system must be capable of carrying the very high short circuit currents that may occur. The equipment has to be able to withstand the thermal heating effect of the short circuit current and also the mechanical forces associated with the flow of the short circuit current through the equipment. Circuit breakers have to be able to close onto a fault, for example when the earthing leads have been left on the power system downstream of the circuit breaker. And also the circuit breaker must be capable of opening to isolate the fault and do this without being damaged itself. Now there are many different standards and approaches that exist to guide engineers to calculate short circuit currents. And these are embedded in the power system analysis software programs which the engineers use. And because of this, the analysis engineers can lose sight of the internal calculations that their software is performing. So for the remaining part of this video, I'm going to talk about what IEC 60909 Method C actually does. Let's begin by looking at a very simple RL circuit. This could represent, for example, one branch of a power system, let's say a transmission line. Initially there is no load connected to this branch, and if a short circuit occurs, then we can simulate that by closing this switch. And as soon as we close the switch, then current will flow around this loop. So after the switch closes at time equals 0, then the following differential equation applies to the circuit. We can calculate the general solution to this first order differential equation, and by considering the initial conditions at time equals 0, we can solve for the constant A which occurs in the general solution for the equation, and then we can do some algebraic manipulation and we arrive at this equation for the short circuit current as a function of time. So what does this equation tell us? Well, we can see that the first term is a constant amplitude sinusoidal current. You can see we have sine omega t plus a phase angle multiplied by a constant magnitude. IRMS is the steady state RMS current once all the transient effects have decayed. The second term is actually a decaying exponential. We can see we have a sine term here, but there's no omega t. So this is a constant times another constant times a decaying exponential. Now if we look at the exponent, if we divide top and bottom of the exponent by omega, then we see that this exponential decay is actually an R over L term. So the DC current decays as the R over L time constant of this branch. Now the maximum value of the DC component will occur when this sine term has a value of 1. And in a power system, the reactance is very often much greater than the resistance. So the X upon R ratio might be 5 to 20 or even higher. And a consequence of this is that the elements of our power system look very inductive, and to get the maximum DC offset in a inductive circuit, then we have to switch at the instant when the supply voltage is going through zero. So the maximum DC component occurs when phi is equal to zero. So we have our AC component, we have our DC component, and we add these two together, and that gives us the total fault current. Now in practice, the AC component will also decay with time, especially if the fault occurs in a part of a network with rotating machines. For the discussion which will follow, we will ignore this effect and we will assume that the AC component is constant with time. So let's look at a simple example. So we have a branch with a reactance of 1 per unit, an X upon R ratio of 10. From that we can calculate the resistance as 0.1 per unit, and we can calculate the steady state impedance as 1.005 per unit. If the applied voltage has an RMS value of 1 per unit, then the steady state AC current is 0.995 per unit. So we now have all the information that we need to substitute into our equation for the instantaneous current, and that's what is shown in this graph here. So the green curve shows the steady state AC solution. The orange curve shows the DC component of current, and we add those two components together to get the instantaneous current, which is this red curve here. Now in this example, our power system operates at 50 Hz. We've switched or applied the fault at voltage 0. So at 10 milliseconds or half a cycle into the fault, we get the maximum instantaneous current. So this is the AC waveform with the maximum DC offset. Now this is the peak current which the circuit breaker or other equipment has to withstand. But this peak current is not the current which the circuit breaker will have to break, and this is because it takes a certain amount of time for the protection system to pick up, detect a fault and send a trip signal to the circuit breaker. So the trip signal might arrive some 50 or more milliseconds after the fault has occurred. And if we look at t equals 50 milliseconds, we can see that the DC component of current has not yet decayed to zero. So what this example shows us is that accurate calculation of the DC component of current is essential when determining both the asymmetric peak current and also the current which the circuit breaker is going to have to actually break during the arcing period. Now let's suppose we have a more complex network, and now instead of having a single branch supplying the fault, we have 3 branches. So these branches all have different R and X values, but when we close the switch, we have a loop through each branch back to the EMF. So this means that we can use our solution to the differential equation for one branch, and we can use this to calculate I1 with the parameters of branch 1, I2 with the parameters of branch 2, and I3 with the parameters of branch 3. So we can calculate I1, I2 and I3 individually, and then we can add them together to get the total fault current. Now if these branches all have different X upon R ratios, then the DC component of current in each branch will decay at a different rate, and consequently the DC component of current in the fault will be the sum of these individual decaying exponentials. So let's put some numerical values to this. So let's make the reactance of each branch 1 per unit, and we can vary the X upon R ratio of each branch. So branch 1 has an X upon R ratio of 5, branch 2 10, and branch 3 20. So as a result of these parameters that we've chosen for X upon R, the resistance of branch 1 is 0.2, the resistance of branch 2 is 0.1, and the resistance of branch 3 is 0.05. We can work out the impedance of each branch. They're all slightly different, but round about 1 per unit. And the applied voltage is 1 per unit, so we can calculate the steady state RMS current in each branch, and they are all slightly different but very close to 0.99 per unit. So we now have all the data that we need to substitute into our equation for the DC component of current in a single branch. And we can do that for branch 1, 2 and 3. And here we see the DC component of current in branch 1, in branch 2 and in branch 3. And it's obvious that branch 1, which has the lowest X upon R ratio, the DC component of current decays faster than the other two branches. We can add these three currents together to give us the total DC current which is flowing into the fault. So the total DC current that we measure here is the sum of these three. And at first glance this looks like an exponential decay, but we now realize that this apparent decay is not produced by a single exponential, it is the sum of three separate exponential terms. Now, when we do network analysis, we might look at this network with three branches and say, okay, we've got three branches in parallel, let's reduce those to a single equivalent branch and then do our calculations. So if we have the same data as we had before, let's do that calculation, and that gives us these parameters for X equivalent and R equivalent. If we now substitute these parameters into our equation for the DC component of current, we get this blue curve. So this is now a single decaying exponential. And when we compare this with the sum of the DC currents which we calculated in the full network with three branches, we can see that the equivalent branch approach overestimates the rate at which the DC current decays. And we can see that at time equals 50 milliseconds, there is actually quite a significant error between the two calculation methodologies. Now, IEC 60909 provides 3 methods to correct for this error. Method A is the so-called uniform X upon R ratio. Now, essentially, it looks at all branches which are feeding the fault. It finds the branch with the highest X upon R ratio, which is the branch where the current will take longest to decay, and it says the current in all branches will decay at the highest rate. So this method can clearly lead to significant errors when calculating the DC component of current. Another method is method B, the equivalent X upon R ratio at the point of fault. Now, method B essentially does exactly what we did in the previous slide. It calculates an equivalent X over R for the reduced network, and then it says, okay, calculate the short circuit current, calculate the DC component of the short circuit current at the time you're interested in, and apply a factor of safety of 1.15. And this can still lead to significant errors. The third method is method C, the equivalent frequency method. Now, what happens here is an equivalent impedance of the system viewed from the short circuit location is calculated, and it is calculated at a frequency Fc. The X upon R ratio used for the DC current calculation is then back calculated from the X upon R ratio that's just been calculated at the frequency Fc times Fc divided by F. Now, this equivalent frequency Fc is a function of time, and as you progress through the different periods of the fault, the value of Fc that you use changes, and the value of Fc that you would use, for example, to calculate the DC component at the time of the peak make current differs from that which you would use to calculate the DC component at the break time. So let's look at this a little bit more closely. The standard tells us that we take the frequency times time, and if it is frequency times time is less than 0.5, then the ratio of Fc to the nominal frequency of the system is 0.4. If we are in the window where the time is greater than 0.5 but less than 1, this ratio of Fc to F is 0.27, and so on for various time windows. So if we convert this now to a time in milliseconds for a 50 Hertz system, so we're looking at 10 milliseconds, 20, 50, 100, 250 milliseconds. And the equivalent value of FC in Hertz for a 50 Hertz system at these times is 20 Hertz, 13.5 Hertz, 7.5, 4.6 and 2.75. And we can also do the same calculation for a 60 Hertz system, and we get these numbers here. So if we return to the 50 Hertz system, basically the value of FC varies as a function of time after the fault, and that's what I've plotted here in this graph. So initially 20 Hertz, then falling to 13.5 Hertz, then 7.5, then 4.6, then 2.75 Hertz. So this tells us how the equivalent frequency changes with time. So for a 50 Hertz system, we've now carried out step 1 of the IEC 60909 methodology. We now go back to our network, and in our network we have the 50 Hertz impedance values. We convert those 50 Hertz impedance values to their equivalent impedance values at FC at the time when we want to calculate the DC component of current. We then combine the parallel branches and their impedances at FC into a single equivalent impedance, and we can call that ZC. And once we have that single equivalent impedances, we can determine an X upon R ratio, which is actually XC over RC, which is the ratio, X upon R ratio of the single equivalent impedance at FC. We then scale back to obtain our equivalent X upon R ratio, which is XC over RC times the nominal frequency of the network divided by FC. And this will be the value of X upon R, which we use in our equation for the DC component of current. We now have to calculate the impedance of each branch at nominal frequency F. We combine all the parallel branches to get the single equivalent impedance at the nominal frequency F. And from that, for a known driving voltage, we can calculate the RMS current. And we're now in the situation where we have all the values which we need to substitute into our equation for the DC current. So IRMS is calculated at 50 Hertz in this example. X over R is calculated from this equation here, and FC depends on the time after the fault has occurred according to this graph here. So let's look at this in a little bit more detail. So here is our example that we've looked at before. So the data is the same. We know the frequency FC varies with time. So for the value of FC which is appropriate in each time window, we calculate the equivalent impedance ZC of these branches in parallel, and that gives us the value that we have plotted here. So that gives us ZC. Once we know ZC and we know the magnitude and angle of ZC, we can calculate the variable x upon r ratio xc over rc, which is plotted here. And then once we have the variation of xc over r as a function of time, we can convert that to the variable x over r ratio that we need for our equation by using this term, which gives us this graph here. So we can see that what method C is doing is increasing the x upon r ratio as a function of time. And if we think about this, increasing the x upon r ratio will decrease the rate at which the DC component of current decays, and that will bring the response back into line with the theoretical calculation that we derived from the differential equations. The other thing we need to do is to formulate the equivalent branch at 50 Hz so that we can calculate the steady state current. So we now have all the information that we need to apply method C. So if we look at the results, we can plot this graph here. So by substituting the values which are appropriate for x upon r over the time scale that we are interested in, then we can plot the DC component of current. And the DC component of current calculated using method C is the green line here. And you can see we have a discontinuity where FC changes as expected. The blue curve is the DC decay we calculated using a single exponential, which we noted caused a significant error. And the yellow curve is the DC component of current that we calculated solving the differential equation for each branch individually and then summing the decays together. So what this example shows is that when we apply method C, the green curve, we get a very, very close match to the theoretical curve that we calculated using the differential equations. So method C doesn't underestimate the DC component of current, and it gives us a very, very close match to the accurately calculated theoretical DC current from the differential equations. Now, of course, normally when we do power system studies, we wouldn't plot out the variation of the current. You know, we would simply select the time of, let's say, 10 milliseconds to calculate the DC component corresponding to the asymmetric peak current, and 50 milliseconds corresponding to the DC component of current at the break time. But this graph shows us that irrespective of the time at which we do the calculation, then method C gives us a close approximation to the true solution. So method C is clearly superior to methods A and B and should always be used when calculating the DC component of a short circuit fault current.